find significant wave height, peak period, average period, and peak direction from CDIP data products. Keep in mind the theories used here are used across the board, but each website, each company may have a couple different nuances that could throw this algorithm out the window, so be extra careful when you approach this on your own. So here's our first website we're going to visit today. It's going to show a lot of data that you might not have seen before, a lot of really cool stuff. Basically, we're going to focus on the full spectrum. And before we get there, we're going to talk about where the full spectrum comes from. And that's with this displacement data. So this displacement data is right here. Vert stands for vertical. M stands for meters. We're going to be working in meters. And here's our time here. From just these two alone, we can say a lot about waves. First things first, there's two methods to get the statistics I talked about earlier of h-sig, dominant period, average period, and mean wave direction earlier. The first method is called zero crossing method. And basically, the data is plotted out. Usually a computer is going to run an algorithm to count each wave, each height, each period, blah, blah, blah. You add them together and you get h-sig and all those things we talked about. But believe it or not, although that's super intuitive, that's not the way it's usually done to get those statistics. What usually happens is you take these data and you run it through an algorithm called a fast Fourier transform. And what's cool about the fast Fourier transform, it gives us a little bit more of ability to talk about these waves during this time period. It gives us a spectrum. This is the plot, and this is called the variance density spectrum. In real life, it should go from 0 to infinity, but I mean, hey, we can't measure out that far, which is all right. The units here are really funny. They're meters squared per hertz, and basically, instead of taking the average of each band, so when I'm talking about a band, it's like there's this side to this side, and in between that, there's this height. So instead of this height being the average, you take the variance, and this variance is of the surface elevation, and it's the average of the squared surface elevation relative to its mean, or in other words, the expected value of 1/2 a squared. That's definitely another talk. That's like many talks probably, but that's where this is coming from. Again, these units are really funny. But now that we have this spectrum, this would-be function, if it were continuous, we can get a lot more statistics than if we were just using this displacement time series. So we're going to take this data. It's available right here, the ST, the full spectrum product, and the two columns that we're really going to use for the majority of this are frequency hertz and energy meters squared per hertz. Here, our frequencies here, and our meters squared per hertz is there. So that's where this plot gets turned into like a tabular format right here. So we'll go to Google Sheets, and we will drop our data right here. There's a really cool function called import data, where you just put the URL, and when you hit enter, it grabs this data. Just wait a moment. A couple moments. Here we go. All right, so these are the stats we're going to confirm using this data. Keep in mind, it's a little bit behind this first page I showed you right here. The time is different, but that's all right because we're not really comparing it to this. Okay, so we're gonna go off this time. And basically, came on like a nice clump of text. We can get these to individual columns by just selecting down to here, and we'll go to data, split text columns, and voila. We've done the hard part, most of the hard part, believe it or not. For today's video, we don't need these columns. We'll delete them right here. And this is from memory. This is our frequency. This is our bandwidth. This is our energy, the meter squared per hertz. And this was the direction. Again, per frequency, you have energy associated with it and a direction associated with it. This is given to us after they did all the fast Fourier transform and stuff. So our goal today was to get hsig, excuse me, hsig, average period direction, or sorry, average period, dominant period, and mean wave direction. To get these top two, we're going to need some more statistics. These are called moments, M0 and M1. The 0th and the first order moment. There's more moments than this. There's even, believe it or not, negative moments. So M minus 1, M minus 2, M0, M1, M2, so on and so forth. M0 and M1 are very important. The use of going up to the M4 is also important, but just for today, we're going to talk about M0 and M1. So basically, there's a formula for these moments, and we'll start with our equal sign. Take the frequency, and you raise it to the power of the moment, so that's just 0. I'll be extra cautious with my parentheses. Then you multiply it by the energy, and then you multiply it by the bandwidth. And I'm only doing it like in this out of order because the way it's written is kind of more intuitive with the frequency times the energy, then the bandwidth. Okay, and you hit enter, and it's actually going to be, for this one, the frequency to the power of 1, because we're looking for the M1 moment. You know, if it was the 20th moment, we'd do the power of 20. Throw my parenthesis in there. And again, we're going to multiply that by the energy, multiply that by the bandwidth. And for both of these, we will populate the formula. So each row multiplies it out, just how we did in this first row. And this is kind of where slicing and dicing comes up, depending on who you're talking to. Basically, we're looking today at this full spectrum, all these observed values, but sometimes it could be useful, especially to surfers, to just take a little slice of the spectrum, maybe from here to here, from here to here, because there's different waves, different swells that could be in the water. Say you have a long period swell and a short period swell, and you want to evaluate the characteristics of that clump versus that clump. But today we're doing the whole entire thing. So because we're doing the whole entire thing, we're going to sum the whole entire thing. So here's all of M0. Maybe I'll make a header for that, sum M0. And we'll also sum M1. Oh. Beautiful. And again, if you're trying to look at those individual clumps, you can add the selected frequencies that you want. So you don't have to add all of them. That's just what we're doing today. And this is, again, one of the benefits of working with the variance as opposed to the average amplitude. The two reasons for that is, number one, energy of a wave is proportional to the amplitude squared. So, I mean, that's what we're working with there. And then the other benefit is, as I just mentioned, or in other words, how does it go? The sum of the variances is equal to the variances of the sum. But it's not the same with the amplitudes. So you can't slice it and dice it if this column were to be the average amplitude per frequency bandwidth. So that's the cool things about working with variance. Anyway, now that we got those two moments, we can use them. Through probability, it's been discovered that hsig is equal to 4 times the square root of M0. Remember, our units are meters. Our average period, believe it or not, is M0 divided by M1. That's a hertz divided by a hertz. Oh, so that's going to be seconds. And for dominant period direction and mean wave direction, these kind of go hand in hand. And really what we're looking for here is where is the most energy? So we'll just do it visually because it's kind of fun, kind of appropriate, I think. There's 3.69. I think that's the biggest value I see. Definitely, well, none down there. If you're trying to automate this, obviously write a formula, but just for fun, we'll do this. So 3.69 is the largest value we see. And the period with that is the inverse of this frequency right here. So we're going to go equals 1 divided by 0.1013. That's going to be 9.87, be units of seconds. And the mean wave direction is just this direction right next to it, which is 316. 316. And the units for this are degrees, true from north. And just like that, we found everybody's favorite stats. Again, like I was saying, if you're a surfer, if you're really trying to chop up the swell, you can do this process per selection of your frequency. And to a surfer, that's really, really important knowledge. Let's check our answers real quick. I'll just load that site again because it's out of screen for you. But here we see, oh, I want to scroll over. Oh, geez. How do I go? Awkward. So awkward. Well, our H6 is good. Our dominant period is good. Our direction is good. And just out of view, it's a 6.55, I promise. So there's 6.55 there. We will declare this victory. Thanks for tuning in. I hope this served you, whether you're a high school student, college student doing a semester project, or who knows, maybe a master's or something doctoral working with waves. This is great stuff. Have fun with it. Bye.